So at this point you might be asking yourself, what are the benefits to using GD&T over traditionally coordinate dimension drawings that use plus-minus dimensions to locate features, surfaces, and control the size of those features and surfaces? We know a lot of industries are beginning to use GD&T for various reasons, and while we don't like to advocate against coordinate dimensioning, we do like to point out the practicality and effectiveness of GD&T when used correctly. And that's definitely important to point out. Using GD&T incorrectly is worse than not using GD&T at all. So let's take a look at a simple example to explain the benefits of GD&T and attempt to address some common misconceptions. Let's picture a bicycle tire and the rim like we see here. As we know, any major deviations in the diameter of the rim could easily affect the riding performance or even shorten the life of the components due to stresses from vibrations caused by the rim not being perfectly round. So what sort of tolerances could we be applied to this rim to limit these deviations if we're using traditionally coordinate dimension drawings with plus-minus tolerances? First, let's define some terminology from the cycling world. The wheel's roundness, or amount of up and down movement as it spins, is its radial trueness. This is the deviation we will be controlling in order to ensure a smooth ride. Now, we've shown some exaggerated deviations in the radial trueness of this rim. However, the industry sets a guideline that a millimeter or less of radial deviation is an acceptable amount. So what sort of traditional coordinate dimensioning plus-minus tolerance would be applied to this diameter to ensure the radial deviations are restricted to 1 millimeter? Typically, a nominal size, like this 576 millimeters, would be listed in some sort of tolerance would accompany it. This coordinate dimension would restrict any radial deviations to a maximum of 1 millimeter total. Now, for those manufacturers out there, does this seem like an irrationally tight tolerance just to restrict form deviation? Let's think about the rest of the assembly and the requirements that might affect this dimension and its tolerance. The tire or tread assembles onto this rim, and most tire tolerances are relatively loose and depend on many variables such as tire type, manufacturer, intended rim pairing, tire diameter, tire pressure, and many more. So let's say conservatively the tire tolerances on average are 5 millimeters diametrically, or plus minus 2.5 millimeters. We'd be able to have a radial deviation of plus minus 2.5 millimeters on our rim before we have an assembly issue with the tread. So to recap here, the form of the tire needs to maintain a maximum radial trueness of 1 millimeter. But the size, as we can see, can vary up and down to a plus minus 2.5 millimeters in order to pair with the tire tread. We need the form, in other words, to remain tight. However, the size can be much looser. How can you allow a larger size tolerance to help out manufacturing without allowing too much radial deviation to be accepted as well? As you might imagine with dimensions and plus minus tolerances, this is an impossible task. Instead, we recommend the use of GD&T. More specifically, for this scenario, we would recommend using the runout symbol. As we'll see later in this course in the runout lesson, this control restricts runout of the diameter to a maximum radial deviation with respect to a datum axis. The datum feature, in this case, will be the axle of the rim assembly, and runout will only control the radial deviation, not the size of the diameter. That's left up to the size dimension. As we mentioned, the diameter of the rim can then be opened and optimized to give manufacturing more tolerance to work with as far as the size of the diameter is concerned. Utilizing GD&T in this scenario not only gave us more tolerance to work with, but it also focused on the exact functional requirements of the rim. Once again, GD&T is giving the most amount of tolerance back to manufacturing and focusing on where the tolerance needs to be, and in this case, that's form, not size. Now, you'll notice in the real world, a rim can be maintained or fine-tuned after manufacturing on what's called a truing stand. Runout is checked by attaching the axle of the tire to the truing stand and then inspecting the radial deviations with some sort of indicator or feeler gauges. The runout feature control frame will refer directly to the datum feature that should be used to create the datum axis for inspection. Size can then be verified in a separate measurement. Let's take a second to debunk a few common misconceptions that we hear about GD&T. Often we hear that my tolerances will be too tight and it'll add cost to the part if I use GD&T. As we saw in this scenario with the size tolerance and the form tolerance of the rim, we were able to open up the size tolerance while leaving the rim roundness or form of the rim where it needed to be. We actually opened up tolerances rather than shrinking them. The next comment we hear a lot is coordinate dimensioning is easier to understand and is able to do everything that GD&T can. Well, as we just saw, separating form and coaxial requirement from the axis is impossible to accomplish with only coordinate dimensions. GD&T allows us to add a new way of thinking and a new way of looking at tolerances to a feature of size. Often this is already how the part is being inspected anyways. And lastly, we hear you should only use it when it's critical or high volume. Again, with this scenario, we see that tire truing is done on an individual tune-up basis and is inherently not a high-volume task by design, but still it's crucial to define the amount of radial trueness acceptable for a rim. As we just showed you, GD&T opens up our eyes to a whole new way of breaking down our control over any given feature. The tire example showed us that there's more to its diameter than just the size. We also had to consider the form, or how circular that rim is. This is a crucial aspect of GD&T. In fact, all 14 GD&T symbols can be broken down into 4 different aspects of control, the first of which is size. Size is the first obvious control. If a diameter has a size dimension and a tolerance on it, that diameter must measure within the stated limits. The size of the feature refers to how big that feature is. Next, we have form. Form, as we saw with the example of the bicycle tire, is focused on shape. How close to the measured shape is that feature with respect to its perfect form? Form has no bearing on size. However, size and form work together to define how the feature exists on its own in free space. They are only concerned with the feature by itself, regardless of its relationship with other features. The next control is location. Location is simply where does the feature exist. It begs the question, where does it exist with the rest of the part? And lastly, we have orientation. Orientation is the control that determines how much a feature is allowed to rotate or tip away from its perfect orientation with respect to other features. So if location is concerned with translation, we can view orientation concerned with rotation. Together, location and orientation will control how a feature is located and oriented relative to other features. And that's where the concept of datums is introduced. Datums are created from other features, and they allow us to set a reference point in order to locate and orientate other features. These four components, size, location, orientation, and form, or slough for short, are the only variables that all 14 symbols will control. We'll commonly refer to slough or size, location, orientation, and form throughout this entire course as we're referencing how all 14 symbols will control these four elements. Some symbols control one element of slough, while others can control all four elements. However, for a feature to be fully defined, all four elements of slough must be controlled in some manner. Otherwise, we're leaving an aspect open to interpretation and not giving full instructions on how far from perfect they can deviate before they must be rejected. We'll make sure to continue to cover these topics throughout the course and show how each symbol can be used to control the four elements of slough. But if there's one thing to remember, it's that GD&T is used to make sure that the part functions properly. GD&T and its 14 symbols allow designers, manufacturers, and inspectors to speak the same language when they're all working on the same part. Everyone's goal is to produce a functional part. Designers should ask themselves, is this tolerance necessary for function? Does it directly restrict the amount of deviation to ensure usable parts will pass and non-functional parts will fail? Are there any unnecessary restrictions I'm adding to this part? Is there any way to open up tolerances in order to help manufacturing? These are all questions we should ask ourselves as designers. Production, fabrication, and machinists will be able to speak the same language as designers and inspectors so they can make the best decisions in their department on how to make the part. The goal is to efficiently produce a part in a manner that results in a functional part. And lastly, it's important for inspectors to interpret the drawing in the exact same manner that designers intended with no room for opinion or interpretation. This ensures that quality sets up the inspection and executes the proper checks to ensure all functional requirements have been met. Again, the primary goal of GD&T is to communicate exactly what's necessary for the part to function properly, nothing more and nothing less. This often means that some tolerances can be opened up or loosened, while tighter tolerances are only kept where necessary.